In this video, I am going to run through the theory behind buffer solutions, firstly looking at how we make a buffer solution and also explaining how they work with a focus on exam language in particular. So a buffer is a solution that's able to resist changes in pH when small amounts of acid or alkali are added. We can make it either from a weak acid and its salt, so I'm thinking something like ethanoic acid, and its salt might be sodium ethanoate minus Na+, or alternatively a weak base, ammonia is a good example, and its salt, NH4+ Cl. So we've got our weak acid and its salt, which is the conjugate base of that weak acid. And vice versa, we've got a weak base with ammonia, and ammonium chloride, or the ammonium ion there, is our conjugate acid. If you're not sure what I mean by the term conjugate, then flip back a couple of videos in this series, and I have a video on acid-base pairs. So by choosing suitable conjugate acid-base pairs and adjusting their concentrations, we can pretty much make a buffer solution with almost any desired pH range. And it's not just in the lab that we come across buffers. The ocean is the ultimate buffer, our blood ultimate buffer system. So really important in nature as well. So let's look at a buffer system in a little bit more detail. I've taken as my example ethanoic acid and sodium ethanoate. I could rewrite this equation in general where I use HA for my acid, reacting with water, to form the anion, the salt, the conjugate base, A-, and H3O+. So I have this system and it's an equilibrium system. In order to explain how buffers work, we're going to make a couple of assumptions. The first assumption is that all of the anion, all of the CH3COO-, all of the salt comes from the salt itself. The reason that we can make this assumption is that, first of all, ethanoic acid is a soluble salt, which means that in solution it's fully dissociated. So it's going to produce a high concentration of the anion, or the ethanoate ion in this particular example. The second reason why we can make this particular assumption is that in this system we are dealing with a weak acid and its salt. So if I were to take ethanoic acid, I know that the Ka is 1.7 times 10 to the minus 5 mole per decimeter cubed. That is a very small number. So I know that in practice very few ethanoic acid molecules dissociate to form ethanoate ions. So we've got a weak acid, so we've got a negligible anion concentration from dissociation of the acid. And we can also see that because it's a reaction or a system that's in equilibrium, that the presence of ethanoate ions, or A-, is actually going to push the position of equilibrium further to the left, which is going to suppress any dissociation of ethanoic acid, or our weak acid. My second assumption, I'm going to change colour here or I'm going to get a little bit confusing. So my second assumption is that at equilibrium, the concentration of HA, or my acid, to all intents and purposes is unchanged. Again, because it's a weak acid, very, very few molecules, 1.7 times 10 to the minus 5, very, very few molecules of my acid are dissociating. I think it's the easiest way to say. So let's put that into words. What we could say, assumption number 2, that the concentration of the acid, so HA, remember square brackets denotes concentration, remains unchanged at equilibrium. Equals M is my personal shorthand for equilibrium. The ability of a buffer solution to resist changes in pH when either acid or alkali are added can be explained by going back to the Chatelier's principle. First of all, let's look at the addition of acid, of H+. So when that happens, the added H+ are going to react with the A-, the salt ions in my buffer solution. So we're going to have these ions reacting with the added acid ions, hydrogen ions, and they're going to react together to form more of the undissociated acid, HA. So essentially, the result is that within the system, the position of equilibrium is shifted to the left. As a result of that, these added H+ ions are being removed. As soon as you're adding them to your buffer solution, they react with A- with the salt ion, they are removed, and if there is no change overall in hydrogen ion concentration, then there is no overall change in pH. So what we say is that A-, or the concentration of salt ions in our buffer solution, they act as a sink for the extra acid added. And so as a result, the buffer system is able to maintain its pH despite small amounts of H+ being added. Obviously, if you were to add a shed load of hydrogen ions, then eventually, once all your salt ions have been used up, then they're no longer able to buffer. We're going to eventually end up with a drop in pH. When we add alkali to our buffer solution, we're essentially adding hydroxide ions. So addition of hydroxide ions, they react with the H3O+, or the H+, if we're writing the shorthand version of this equation, to form water. So OH- plus H3O+ is going to form 2 water molecules. This will cause the position of equilibrium of my buffer system to shift to the right, which means that more of my acid molecules that I have in my buffer solution are going to dissociate, and as they dissociate, they are going to produce, well, let's have a look what happens when this dissociates, they're going to produce more hydrogen ions. They're going to essentially replace the hydrogen ions or the oxonium ions that have been neutralized by reacting with the hydroxide ions that were added. So what we say is that the concentration of the weak acid in my buffer solution is a source, or sometimes you see this written as a reservoir or described as a reservoir of extra hydrogen ions. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the description below, it'll take you straight to Crunch Chemistry School, where you can access my free maths skills course, complete tuition, and worksheets designed specifically to build your confidence and stretch you. Together we can do this.